Standard model effective field theory. All right, so let me just start by saying thank you very much to the organizers of this event for putting together such a wonderful conference. It's a pleasure to be celebrating with you 50 years of successes of QCD, and most importantly with many, historical figures. So it's an honor, and thank you. So for us, for me, they are historical. So. All right, so given the nature of the conference, I wanted to start by reviewing with you some of the lessons we have learned from QCD and the enormous progress we have made there, and how this is now guiding our research for ever more subtle deviations from the standard model. So we'll go together through some of the progress we have done in precision predictions, and then I will discuss how they are being now applied in the context of effective field theory interpretations for new physics searches at the LHC and elsewhere. Okay, so let's start with the big picture. The ultimate goal of the precision program is to determine the Lagrangian of nature. And so far, we have discovered the terms that correspond to the standard model Lagrangian. Our standard model Lagrangian is simple enough that you can fit it on a coffee cup. You have gauge terms for each standard model gauge group, the kinetic term for the fermions, Fermi-Yukawa couplings, and you have the potential that we are still trying to measure for the Higgs. And so to discover anything beyond these terms that hasn't been obvious, like a resonance peak, we need to understand the standard model predictions very well. And so I will be focusing in the first part of my talk on the QCD part of this Lagrangian, given the outsized role that it plays in this precision program. Okay, so why is QCD so important? One reason is due to the fact that the QCD coupling is the strongest of the standard model gauge couplings at the energies we are probing, for example, at the LHC. And so typically our perturbative QCD corrections tend to be larger than electroweak and QED corrections. And so this is one of the plots that I like to show quite often. It shows the running of the strong coupling constant, and it shows it over 10 orders of magnitude, anywhere from near 1 GeV to 1 TeV. And what you can see immediately is that there is a remarkable agreement between the prediction of the running and the measurement. And as we go to higher values of the energy, to the higher energy region, we see that the strong coupling constant decreases, and that's exactly what allows us to calculate perturbatively in QCD. So the decrease of alpha S with energies is what led to the Nobel Prize in 2004 for Gross, Palizzo, and Wilczek, which is something we are proudly celebrating today in this conference. Okay, so what is the current state of the art? I wanted to show it or give you an idea through this plot from Atlas, which is Higgs related. So they show you here various production modes for the Higgs, but the dominant one is the gluon fusion. And the theory prediction is shown here in gray. You could see that the theory prediction, the uncertainty is already a large fraction of the total experimental uncertainty. This is very interesting because the prediction you see in here is a next to leading order in QCD. So it's really a high precision. However, the precision of our measurements is so high and continues to improve that it puts immediately pressure on the theory predictions to keep improving. So this plot to me shows really the importance of perturbative QCD for the high energy physics program. Okay, so let's talk about confinement in QCD. Confinement in QCD binds quarks and gluons into hadrons. So now we are looking at the plot of alpha S, and we are looking at the lower energies region where the strong coupling constant is strong. And so understanding the distribution of these patterns in the proton through QCD is a critical component of the HEP experimental program. And that brings us to talking about pattern distribution functions. PDFs are non-perturbative objects, as we all know. However, even there, the precision of our perturbative QCD predictions come in. PQCD there comes in two different ways: through the understanding of the running of the PDFs with the factorization scale, and also, because they extract these PDFs, we need processes for which a prediction is required. And so this is a plot from the NM-PDF collaboration. It shows you the gluon PDFs as a function of Bjorken X. And you can see here the difference between the NLO and the NNLO extractions. You can see that here in the high X region, there is a difference between the two extractions. Now, this large X region is sensitive to new physics effects. So we need to understand it very well. And so this is one reason why we have to keep improving our PDFs as well. Okay, so what's the next stage for us? The next stage is to learn what solves outstanding problems in nature. We have many open questions, the dark matter, neutrino masses, the hierarchy problem. And so we want to understand what terms should we add to the Lagrangian to answer some of these questions. So far, we haven't seen any new particles, and so we could organize the search through the approach of effective field theory. And so in this EFT approach, what we do is expand the powers of the probed energy over the scale of new physics lambda, or standard model masses over lambda. And just as an example, the lowest dimension operator we can, for example, add to this Lagrangian is this unique dimension 5 operator, which gives masses to the neutrinos in the standard model. But it does that at the price of violated lepton number, and that's something we can look for experimentally, for example, through neutrino-less double beta decay. So this example pretty much tells you the philosophy of this EFT approach for new physics searches. Write down an operator and look for its experimental consequences. But given the fact that the data we are using has high precision, and we continue to improve this precision in various ways, for example, we are also thinking of future colliders, we are inevitably led to improve our predictions in this effective field theory framework as well, just like we do in the standard model. Okay, so this brings me to summarizing the goals of this talk. I will briefly review examples of the precision program in QCD, both in its historical successes and current status. I will be focusing on perturbative calculations and higher orders. I will discuss how similar issues of higher order calculations arise in the EFT extensions of the standard model, in particular focusing on the standard model effective field theory. And finally, I will discuss open questions in the precision study of SMEFT and summarize new ideas on how to approach them. Okay, so let's start with the precision of the standard model part. So this is all known. It's just a brief review. To calculate our cross-sections, we rely on the concept of factorization. So our hadronic cross-section, we write them as a convolution of PDFs, which are non-perturbative objects. We extract them from data, but then they are universal. We can use them to calculate any other process. Times a Platonic cross-section, which is process-dependent, but we can calculate it perturbatively. And this is true up to some power corrections in Radja QCD over the scales we are probing. Both of these quantities have a dependence on physical scales. For example, the Platonic cross-section depends on the factorization or renormalization scale. So one reason for us to go to higher orders is to minimize the dependence on these physical scales. Okay, so I will be focusing in this talk on computing the Platonic cross-sections to as high as we can in various couplings, QCD, electroweak, or the BSM couplings. And so, for example, in QCD, our expansion of the cross-section in alpha S is written this way. As I said, we try to include as many terms as we can to reduce the dependence on physical scales. The first quantitative term in this expansion that is needed for reliable predictions is the next reading order. And so what I want to do here now is review the importance of this first term, and I would start with a historical example. So this is an example that Keith has already showed you yesterday, but I'd like to show it because of its relevance and its importance. At CERN in 1979, Na3 experiment, which was measuring the dimuon invariant mass of the Drell-Yan process using a proton-nucleon scattering, observed that there is a deviation between our prediction and the data. And so data is here. The prediction, which was back then a leading order cross-section, which was obtained using a CDHS parameterization of the PDFs, was away from the data with this shown in this solid line. And to make the two agree, one has to multiply the prediction by a constant factor of 2.2 for this proton-nucleon scattering. And this experiment was repeated again, for example, with an n-type proton-nucleon scattering. A similar k-factor was needed for the two to agree. This was, by the way, one of the first instances where the notion of a k-factor was introduced, in this case to make these two agree with each other. Okay, so Keith and Martinelli and Altarelli decided to sit down and calculate the next term in the expansion, the next reading order correction in QCD. So what you see in here is the pure NLO correction normalized to the leading order cross-section as a function of tau, which is the invariant mass squared over the center of mass energy. And there are many curves in this plot, but the one to focus on is the one denoted as total, which is the sum of all the Platonic channels. And what you can see is that these NLO corrections increase the leading order result by 80 to 100%. And so when we write the full cross-section, which is the sum of the leading order cross-section plus this NLO coefficient, we get a factor of roughly 2, which significantly reduces the tension between data and theory. So this calculation has early on emphasized the importance of higher order corrections in correctly interpreting our data. And so the discrepancy here was resolved by this next term in the expansion. Okay, so that was in 1979. Decades later, we are much more advanced. So today, we have codes that allow us to calculate next reading order QCD corrections, electroweak corrections in an automatic way. For more complicated processes, we even know how to combine these fixed order predictions with Monte Carlo pattern showers to resum large logarithms in the soft and collinear regions of jet phase space. And this is just one example of such results. It's coming from the MATGraph AMC at NLO. All these processes can be calculated in an automatic way. But you can see you can do that for up to 4 particles in the final state. You can actually do better, even more, with dedicated codes. You can go up to 6 particles in the final state. And an example of that is the work done by Black Hat plus Sherpa collaboration, which Zvi and David Kosover are members of. So this collaboration also has produced many results. I'm just showing you one sample here. This is W plus 5 jets, an important SUSY background. And you can see that just by writing down the diagrams here, the complexity of this process. Many kinematic variables, getting stable numerical representation in all these kinematic regions is a challenging thing. So the result of what they did is shown in this plot. This is the cross-section as a function of the scalar sum of the transverse energies in the final state. And what you can see immediately from the gray band is that the uncertainty is much, much better than what we had it at the previous order, the leading order. And that's reducing this uncertainty is important for the phenomenology. Okay, so that was one example. Another example comes from the Sherpa collaboration, and it also illustrates the current state of the art. We are able now to combine fixed order results with pattern shower. And this is an example of PP to W plus jets, where we are looking at sample of W plus 0, 1, and 2 jets. In one case here, we have included the next reading order QCD corrections. In the other case, we have added also electroweak effects. And so what this plot shows you, this is the cross-section as a function of the PT of the gauge boson, is that if you look at the bottom part, which is normalized to the next reading order QCD corrections, you can see that the electroweak effects play an important role in the higher PT region of the gauge boson. So this is an important observable, of course. It's used in the extraction of the W mass, admittedly in the region around this area here. Electroweak effects are smaller there. But in general, because we are also doing new physics searches, it's important for us to include these effects. So I would say that the standard model at NLO is fully ready now for current and future experimental data at NLO. So let's move to the next reading order at QCD, and I will start again with some historical examples. Early NNLO corrections were actually done for Corot singlet processes, such as Drelian and Higgs. And so the observed corrections had basically 2 trends. We see that NNLO corrections are needed to make the most out of our data because data was precise. And also the corrections can sometimes be surprisingly large. And so these are 2 examples. The left is the Drelian, neutral current Drelian at the tevatron, so PP bar here. Cross-section as a function of the rapidity of the final state here. And what you can see here clearly is that NLO alone would not have been enough when we were compared with data. We needed NNLO. But what's interesting is that the precision of the data is good enough that we are able to distinguish between 2 different NNLO predictions, which were obtained here using 2 different PDFs. So this immediately tells you can use that to improve your PDFs. It tells you that you have to go and work on improving your PDFs. On the right-hand side, we have Higgs production in gluon fusion mode. We are looking at the K factor there. And what you can see is that in going here from the leading order to the next leading order, corrections increase by 75%, depending on the value of the Higgs mass that you use. So this was one of those examples that have shown that NNLO corrections can be large for some processes. Okay, so for us to go to higher orders, for example, go up to NNLO, we have to deal with the infrared singularities in our matrix elements. And dealing with them becomes more complicated as we go to higher orders, and in particular when we include jets in the final state. And so it took us a while to understand how to best organize the extraction of these infrared singularities, decades, in fact. The good news is that now we have multiple methods to do this. I show you some of them here. Antenna subtraction is one of those methods. It uses physical processes to construct infrared counterterms. Thomas probably will cover this in his talk, so I won't go into any details. There is a number of local subtraction schemes that have been derived by various groups in the community, including color for NNLO, sector improved residue subtraction, which is an evolution of the original sector decomposition method, projection to Born, nested soft collinear subtraction, which is also an evolution of the original sector decomposition method, and local analytic sector subtraction. So those are local methods. There is another approach which is conceptually different from the ones I have showed on the previous slide. It uses the fact that we understand to all orders in alpha S the behavior of QCD in the singular regions, the resummation and effective field theory. And so we can use all order resummation to calculate the cross-section, for example, at next to leading order. And so to describe this, I will focus on a method called angiotenous subtraction. Sometimes it's called angiotenous slicing because of the way it works. So the angiotenous method is actually based on an event shape variable, which is called angiotenous, which was introduced in 2009 by Ian Stewart and collaborators. So this angiotenous has a very simple definition. So you start by defining your light-like directions for the initial state beams and final state jets. And then you calculate the scalar product of the momenta of the partons in the final state with these hard directions. And what this minimum here means is that you are trying to look for to which of these hard directions your partons are closest to. And you're doing this for every parton in your final state. And the result of this is going to be one of two. And so this will be, you get one of these two options. Either you find that your angiotenous is very small, and that tells you that all your radiation is either soft or collinear to the hard directions, beam or jet. This is what we call unresolved. Or you find that tau n is greater than 0, and that tells you that at least one additional jet beyond your Born level is actually resolved. Okay, so what you do is you introduce a cutoff, tau cut, that separates these two regions. Below the cutoff, you use the resummation formula, expanded up to a certain order in alpha s, for example, alpha s squared for n and all calculations. Above the cutoff, because we have established that tau n is greater than 0, we know that we have at least one additional jet beyond the Born level. All we need is just a next leading order calculation for the Born process plus an additional jet. And there are plenty of methods that tell you how to extract infrared singularities at NLO. Now, below the cutoff, the resummation formula has power corrections. However, one can improve the dependence on these power corrections by calculating them analytically. And in fact, there was some work in the literature that was done in this direction. People have also played with different definitions of the angiotenous to see if there is a definition that is less sensitive to the power corrections, and I refer you for that to work done by Ian Stewart and collaborators. There is another approach that works in a similar similar way. It's called QT subtraction, which was the first of these two methods. QT subtraction, however, does not work for processes with jets in the final state. Okay, so these methods have been used by our community to provide many predictions at next to next leading order for 2-to-2 processes. Just to show you a few, this is a sample. We have Z plus jet using angiotenous. We have photon plus jet using antenna, TT bar using sector improved residue subtraction. In all these cases, you can see clearly that at N and O we have smaller uncertainty, we have better agreement with data, and so that was good progress. Okay, so the fact that we have an ever-increasing quality of our LHC data, and also from our expected future experiments, means that we have to keep innovating in perturbative QCD techniques. So today we know how to calculate next to read order corrections for color singlet processes, which is the situation we were at, a little over a decade ago when we were able to calculate, for example, Dreliant at N and LO. Now we are able to do these things at N cubed LO. So this is a plot that shows you the ratio of K factors for neutral current to the charged current as a function of the invariant mass Q here. And the plot speaks for itself, I would say. You could see that really we have now very well, remarkably behaved perturbative QCD theory in this, for this process. And you can also see that there is no residual theoretical uncertainty since the error band is completely contained within the NNLO result. So you can use this result as a benchmark to improve your PDFs. You can use it as a benchmark to improve your or understand your systematic uncertainties. This is another example that shows the current state of the art. This is Higgs production at the n-cubed LO level by Boughezal and collaborators. Again, here we see an excellent convergence of the perturbation theory. And this is an important result. It will be of prime relevance as we continue to understand the properties of the Higgs at the high luminosity LHC. Okay, so you can actually complicate life in perturbative QCD in two different ways, either by adding loops or by adding legs. So many of the examples I showed before were focusing on adding more loops. This was one of the examples where our community was able to get a first result for a 2-to-3 process. This here we are looking at the ratio R32, which is a ratio of 3-jet to 2-jet cross-section. If you recall the alpha S plot, this is actually one of the observables that goes into the understanding of the running of alpha S. So what you can see clearly from the bottom part of this plot, which is a ratio to NLO, is that these NNLO corrections can be as large as 20% in the lower region of the PT of the leading jet here. And then as we go to higher values of the PT of the leading jet, these corrections decrease. So overall, again, NNLO corrections here were important for this observable. Okay, so that was precision for the standard model. I would like to move now into precision for new physics, and I will introduce the standard model effective field theory, and then some related open questions. So what do we learn from the remarkable success of the standard model precision program combined with the null search at our colliders? I'd say our data suggests, although it does not demand or require, that there is a mass gap between the standard model and new physics. And so this is a cartoon plot that summarizes I would say, the situation we are in right now. Suppose the maximum energy we are able to probe is Mmax, and suppose the scale of new physics is lambda, which is sitting here. If it's too far above what we are able to probe today, we will not be able to see this resonance peak, but we might be able to see deviations from the standard model. But that requires us to understand the standard model predictions pretty well. So that's one of the motivations for our community to continue to improve our predictions. Our hope, of course, is that lambda is not too far away from Mmax. Okay, so there is an effective field theory framework which incorporates this point, and it's called standard model effective field theory. It assumes the standard model field content and gauge symmetry, and it includes all possible higher dimensional operators which are suppressed by scale lambda. Now, in all the analysis I will be showing you later, we neglect odd dimensions operators because they violate lepton and baryon numbers. And so when we write the Lagrangian, the first term is going to be a dimension 6 operators suppressed by powers of lambda squared, and then they are followed by dimension 8 operators suppressed by lambda to the 4th, and then you keep going on to the higher dimensional ones. So the assumption here is that this lambda is much larger than the energy we are able to probe at our colliders. It's much larger than the Higgs vacuum expectation value. And if we are comparing experiments with disparate energies, we need to use renormalization group running. Okay, so I would say that it's the first statement to say that the development of this SMEFT as a fully consistent quantum field theory ready for comparison with data, including higher order effects and renormalization group evolution, is a great success of our community in this last decade. Today, we have the full basis at dimension 6. We understand the renormalization group running at dimension 6. We have the full basis at dimension 8, the full basis at dimension 10, and there are some first results for dimension 12. And what's nice about it is that it really accommodates a rich spectrum of phenomenology in all sectors. And this is just here showing you what the dimension 6 basis looks like and how it categorizes the different interactions. Okay, so a nice feature of this SMEFT is actually that it motivates experimental analysis by identifying new observables to study. And so one thing we have looked at is the Durian process, taking into account some dimension 8 effects. And it turns out that they lead to some angular structure in the Durand process, which motivates an extension of the decade-old angular basis that was used on the experimental side. And so if you calculate your cross-section as a function of the lepton angles theta and phi, let's say we are first in the standard model, so we are looking at all these terms outside the red box, what you get is terms spherical harmonics with an angular momentum of up to j equals 2. This is at leading order. This picture does not change when you add higher order QCD effects. It is minimally violated by electroweak effects. Now, when you go to SMEFT and you include dimension 8 effects, we find that there is a category of operators that leads to spherical harmonics of angular momentum j equals 3. And so this is what requires you to extend the basis that was used previously on the experimental side. And so if I take the leading term in this expansion, which is B0, and then I go and plot the effect of the various operators as a function of the invariant mass of the leptons by turning on one Wilson coefficient at a time just to see the impact of each of these operators, what you see is that these operators lead to large effects at high invariant mass values. And most importantly, they grow quartically with the invariant mass. And like the standard model contribution, which is shown here in this dashed line, which grows logarithmically. So this is a smoking gun signature for new physics, and we really look forward to our experimental colleagues reanalyzing their data to look for such effects. Okay, so there is right now a rich program that exists to search for SMEFT-induced deviations across energy scales. There's a lot of effort and activity going on the theory side and on the experimental side. Most natural experiments to look for SMEFT effects are higher energy experiments, simply because we expand in E squared over lambda squared. So at higher energy, you should be more sensitive to these new physics effects. And this is an example of one of the global fits that were done by some members of the theory community, John Ellis and collaborators. They are looking at various Wilson coefficients here, Higgs related, and they are trying to see what effective new physics scales you can get. So 3 bands here refer to the fact that I'm using 3 different sets of data. The solid lines here means that when they put bounds on a specific Wilson coefficient, they marginalize over the other ones, meaning they let them vary. And the empty ones just refer to the fact that we put the bounds on this Wilson coefficient, setting everything else to 0. So the marginalized bounds are always weaker than the other bounds. So overall, the LHC is making great progress in probing the parameter space of SMEFT. However, there are many open questions that one has to keep in mind when interpreting the data in this framework. And I will try to raise some of them and give you what we've been doing to address them. So let me start with open question number 1. Many of the questions we have confronted in QCD play out again when we look at corrections in SMEFT. For example, do we have control over the expansion 1 over lambda? Right now, when you look at SMEFT, you have expansion 1 over lambda in addition to the expansion in the order coupling constants. And so what I wanted to show you from this plot, which is by the SMEFT collaboration, is the importance of expanding or including higher order effects in the 1 over lambda squared expansion. So what they are showing you here is a bunch of SMEFT operators, and they are putting bounds on the corresponding Wilson coefficients. And let me focus here on the stuff inside this blue box. You see 3 bands. The blue band corresponds to truncating SMEFT at order 1 over lambda squared, so taking only dimension 6 effects, while taking NL or QCD effects into account. The red one goes 1 order further, so it's 1 over lambda to the 4th, coming in this case from dimension 6 squared, but we have leading order effects. And then the gray one is dimension 6 squared, taking into account QCD effects at NLO. So the first thing that we can look at is what is the impact of QCD effects. For that, we are going to compare the gray and the red bands. They are both at order 1 over lambda to the 4th. One is next leading order in QCD, the other one is leading order in QCD. You can see that the impact of QCD effects here is minimal on the bounds. But then if you compare the order 1 over lambda to the 4th with order 1 over lambda squared, so truncating at dimension 6 versus going to dimension 6 squared, you see that the difference in the bounds is an order of magnitude. So here, going to higher order in 1 over lambda squared is important, in fact, more important than the QCD effects. In this orange box, what they show you is that there is a subset of operators that do not interfere with the standard model. They only interfere with themselves. And what that means is if we truncate our expansion at dimension 6, we will miss this whole set of operators. So this really emphasizes the importance of going to higher orders than 1 over lambda squared. Let me show you that in terms of some new physics, 2 examples of new physics models, starting with Z prime. Here I want to address the question, are dimension 8 terms in SMEFT important for the data sets we are considering, and can we distinguish them from dimension 6 effects? The thing is that different UV models have a different sensitivity to these dimension 6 and dimension 8 effects. For example, if I look at the Z prime model, and I expand the Z prime propagator in the limit where p squared is smaller than the Z prime mass squared, I have contributions at dimension 6, at dimension 8 as well. So when I write down my cross-section in SMEFT, you have the interference of the standard model with dimension 6 suppressed by lambda squared. At 1 over lambda to the 4th, you have 2 terms, dimension 6 squared, and the interference of dimension 8 with the standard model. In this particular case, I have contributions from all these terms. Now, if I look at the KK graviton, for example, the KK graviton starts immediately at dimension 8. And so when we write down the cross-section, the only contribution that we get is from the interference of dimension 8 with the standard model. So if we were to neglect dimension 8, we will miss this subcategory of models completely. So what I wanted to emphasize here is that it's important for us to not neglect these effects. It's important for us to keep dimension 8, measure it, find observables that allow us to distinguish dimension 6 from dimension 8 effects, and then use it as a diagnosis tool for different UV models. And so let me move to open question number 3. There are right now several exciting potential deviations between precision predictions of the standard model and experiment. Can the EFT approach guide us to alternative measurements that can shed light on these deviations? And so one of these deviations is associated with the Mionji -2. We can't reconcile the theory prediction with the measurement. But it turns out that the dipole operators that lead to the Mionji -2 in SMEFT also lead to subleading 1 over lambda to the 4th effects in the Drolian process. However, the relevant operators or Wilson coefficients are weakly probed at the LHC. So the relevant ones are in this red box, and in particular, the so-called CEV is very weakly constrained. So the question is, are there other experiments or other observables that will allow us to probe this parameter space in a better way? And so we'll show you examples later where this is actually possible. So let's talk about some new ideas in the SMEFT. One of the analyses that we have done with the most recent 13 TeV Drolian, invariant mass and forward-backward asymmetry, illustrated 2 points. One of them we have already seen it. Higher order terms in the SMEFT expansion can be important in our fits. The other message is that sometimes it's important to use multiple data sets to get better constraints on our Wilson coefficients. And so this is an example where we are looking at 2 dimension 6 Wilson coefficients from 4 fermion operators, semi-leptonic 4 fermion operators. And we look at the impact of the invariant mass from Drolian at 13 TeV, truncating our expansion at dimension 6 squared. We looked at the forward-backward asymmetry, also truncating our cross-section at dimension 6 squared. And then in red, we looked at the combined fit. And we did that actually for both, truncating at dimension 6 squared and dimension 6. So what you can see immediately from this plot is that if we were to rely, for example, only on the asymmetry, we have degeneracies in this parameter space. The blue actually shows you what we can get from using just the invariant mass of the Drolian. But then if you combine the 2 fits or the 2 data sets, you can get a much better constraint on your Wilson coefficients. So in this case, contrary to the impact of higher order terms in the SMEFT expansion on fits requires us to use multiple data sets and observables, and they happen to be, in this case, from the same experiment, LHC. Now, there are other situations where this doesn't help. This is an example where we look at the dimension 6 operator and its dimension 8 extension. And you can see 2 types of fits that are done here. The vertical and horizontal lines or bands correspond to the case where you only turn on one of the Wilson coefficients and you set the other one to 0. And so looking at the combined fit, which is in green, you can see that you can get, in that case, much stronger bounds. So this is for turning here CLU only on and setting the dimension 8 Wilson coefficient to 0. and they can do the same with the dimension 8 Wilson coefficient, turning it on, and the other one setting it to 0. Now, if I turn both of them on at the same time, I get much weaker constraints on these Wilson coefficients. Red is the invariant mass, blue is the forward-backward asymmetry. In both cases, you see degeneracies. And here, even after combining the two data sets, we still have some degeneracy in our parameter space. So here, to distinguish between dimension 6 and dimension 8 effects, we need to go beyond LHC data. And so this brings me to talking about low-energy experiments. These high-intensity, low-energy experiments can help us distinguish between dimension 6 and dimension 8 Wilson coefficients. The reason is that because we are expanding E squared over lambda squared, low-energy experiments are going to be less or not sensitive to dimension 8 effects, which are proportional to E to the 4th over lambda to the 4th. So what you could do is use them to constrain your dimension 6 parameter space and let LHC data focus on the dimension 8 parameter space. And so in the next few slides, the analysis that we will be doing focus on these 4 fermion semi-leptonic operators at dimension 6, and these are their dimension 8 extensions that give non-vanishing contributions. And we'll be talking about parity bilateral experiments. Those typically organize their studies in terms of axial and vector axial currents, but you can actually translate this notation to the SMEFT notation by just rewriting your vector and axial vector currents in terms of the left-handed and right-handed currents. Okay, so one of the low-energy experiments we have looked at is called P2. This is a proposed experiment in mines. It's an elastic electron scattering of a hydrogen or a carbon target. And so what they measure is the combination 2C1U minus C1D. And because they are not sensitive to the dimension 8, when you use their data to put bounds on this parameter space, you get very strong bound on this dimension 6 combination. With the LHC data, if you use the invariant mass, this is the kind of constraint that you can get. LHC is sensitive to both dimension 6 and dimension 8. And so you get these elongations which tell you that there is a degeneracy in this parameter space in this blue shape. So now if I combine both data sets, LHC and P2, I get this red ellipse, which gives you much stronger constraints on this parameter space. So here P2 is helping you distinguish between dimension 6 and dimension 8 effects. There is another lower energy experiment that is coming up soon. That's the electron-ion collider at BNL. This will be our first high-energy DIS experiment with the ability to polarize both the electrons and the protons. And this will, of course, open a new window into understanding QCD. So these are the parameters of this machine. It will be roughly 140 GeV center of mass energy, 70% polarization for the protons or the electron beams, a luminosity of up to 10 inverse femtobarn. These are rough parameters. And so you can see, for example, our current understanding of the polarized gluons and the polarized quarks. It's not really great. EIC is projecting to improve this understanding significantly, hopefully when it starts operating. And so we'll be looking here at the DIS process. So these are the kind of diagrams that will be contributing. So just to show you what the SMEFT cross-section looks like from the photon contribution from the previous diagrams, this is the expression for the SMEFT cross-section, and you can see that it depends explicitly on the polarization of the protons and the leptons. And so by turning on and off these polarizations, we are able to construct different polarization asymmetries, and those asymmetries have a sensitivity to different linear combinations of the Wilson coefficient than what we have at the LHC. So the idea here is that once you combine the two, you will be able to remove degeneracies that the LHC alone cannot remove. Okay, so this is one of the studies that we have done. We have used here the polarized lepton asymmetry and compared the kind of constraints you get from there on dimension 6 operators with D4, which is simulated EIC neutron data. We are looking at also P4, which is simulated proton data at EIC. And we also look at nominal luminosity versus high luminosity, where the high luminosity for the EIC would be roughly 100 inverse femtobarn, so a factor of 10 than the nominal luminosity. Okay, so you can see clearly just by looking at the left plot here. Sorry, this pointer is very hard to control. you can see here that the LHC band is showing you a strong correlation between these two parameters. This is what you get from the neutral current Giuliani invariant mass. If you look at D4 or P4, both of them lead to much stronger constraints on this parameter space. P4 in this case provides stronger constraints than D4. We looked at also taking P4 since it's providing the strongest constraints. Check the impact of high luminosity versus low nominal luminosity. You can see that the bounds do not change by a whole lot. I mean, already with P4, with nominal luminosity, and even D4, you're able to do much better than the LHC in this case. Okay, so we also looked at the impact of future proposed machines like FCCH and LHEC. And in this case, besides the 4 framing operators, we also look at vertex, Z-vertex operators. And so you have a 17-dimensional parameter space in here. And so these are examples of two vertex Wilson coefficients. In this case, electric precision observables in green show you the strongest bounds on the stronger bounds than the EIC on this parameter space. However, the bounds coming from LHEC and FCCH are so strong that you need to zoom in so closely to see how well they can constrain the parameter space. So both of these machines are powerful machines. FCCH is, of course, the winner in this plot, but you can do a lot also with LHEC. Okay, so I want to discuss another thing, the transverse spin asymmetries as new observables to understand our parameter space. So new colliders offer new measurement possibilities with a new sensitivity to BSM physics, and one of these examples is actually the transverse beam polarization asymmetry at the future EIC. So this is how it is defined here. When I say ATU, it means we are transversely polarizing the lepton. The proton is not polarized. So you're looking here at the difference of cross sections for positive and negative polarization of a single beam transverse to the beam direction. And so in the standard model, this happens through two mechanisms: the photon box, the exchange of two photons, and the tree-level Z diagram. And so if you calculate the asymmetry, for example, from the photon box contribution, this is what you get. The relevant terms are the ones in here. You see that we are doubly suppressed by the ratio of the lepton mass to the momentum transfer and alpha QED. And you see also that we have dependence on sine phi. This is the transverse plane azimuthal angle between the initial state lepton polarization and the final state lepton direction. This is kind of a hallmark for these transverse spin asymmetries. So that's from the photon box. The Z contribution will look similar to this, except that you will not have the suppression with alpha QED. So let's plot them. And this is the plot for the standard model as a function of Bjorken X. Red is the Z, green is the two photon contribution. The most important thing that you should notice here is that they are proportional to 10 to the power minus 6. So that's an extremely small asymmetry in the standard model. And that's exactly what makes it an excellent challenge for new physics searches. Okay, so what kind of new physics can modify the transverse spin asymmetries? This will be discussed here in the context of SMEFT, of course. And we will look here at SMEFT operators that do not have the explicit lepton mass suppression. And with an explicit calculation, we find that these operators are the dipole operators that are shown in here. And I will focus on the first two, the lepton dipole operators. We have lepton and quark ones. I'm focusing on the lepton ones in this discussion. And so if you calculate the asymmetry, you get a long expression in SMEFT. However, the relevant factors, I highlight them in blue here. In particular, so the Wilson coefficients are complex numbers. They have real and imaginary parts. So the real part of this CEZ exponential minus I phi will be the sum of two terms. Cosine phi times the real part of CEZ plus sine phi times the imaginary part of CEZ. And I have a similar expression for CE gamma. So you can see that we are sensitive to both the real and imaginary parts of the Wilson coefficients. And most importantly, this coefficient of cosine phi gives you the anomalous magnetic moment, and the real and the imaginary part gives you the electric dipole moment. And so we are sensitive to these operators that govern the anomalous magnetic moment and the electron dipole moments, and we can probe them separately using this observable. And the fact that we have a small standard model background makes it really an optimal probe, new physics probe. Okay, so let's plot the coefficient of cosine phi, which corresponds to CEZ, as a function of the Bjorken X. And so this is what you get for various choices of Q. But what you can see is for Q30GeV, you can get an asymmetry of the order of 10 to the power minus 3. This is 3 orders of magnitude higher than what we have in the standard model. So you can actually use this to probe CEZ. On the other hand, we also have a new physics contribution in SMEFT for the electron G minus 2. This was calculated by Manohar and collaborators, and this is what you get. And what you notice is that this measurement will be mostly sensitive to CE gamma because CEZ is suppressed by a factor of 100 compared to CE gamma. It has 10 to the power minus 5 compared to 10 to the power minus 3 for CE gamma. And so when you combine both of these measurements, you will be able to probe the parameter space better. There is a proposed upgrade of the EIC, which involves replacing the electron beam with a high-energy muon beam. And this will be the first step towards a high-energy muon-muon collider. The parameters of the machine are actually shown here. 960 GeV muons with 275 GeV protons. We assume 50% polarization, 50 integrated luminosity, 50 inverse femtobarn of integrated luminosity. And again here, if I plot the coefficient of the cosine phi as a function of Bjorken x, I see that there is a number of values of Q for which the asymmetry is actually large. And so you can probe the operators that lead to the muon G minus 2 using this particular measurement. And again, here in SMEFT, we have an expression for the muon G minus 2. And again, you notice the same pattern here. We are primarily sensitive to C mu gamma through this measurement. And so combining the two measurements will allow you to probe the parameter space for the muon G minus 2. And in fact, this deviation could be accommodated by a region of the parameter space where C mu gamma is of the order of 0.01 C mu z. It might look like random factor, but it's actually a loop factor here. And so transit spin asymmetries here at muon-ion collider can probe the same parameter space as the muon G minus 2, which is interesting. So that's it. This brings me to the conclusions. The precision study of QCD has had a profound impact on our understanding of nature. The lessons we have learned and over the decades continue to guide us as we continue our search for the new standard model. And may the next 50 years be as successful as the previous ones. Thank you. Yes.
Yeah, we have time for a couple questions. Maybe you do a question, then you second.
Are you starting?
So in the discussion of near future machines, what, if anything, will we learn from high lumi LHC?
So from the high luminosity LHC, so you're talking in respect to probing the SMEFT parameter space or just in general? Because this is a big question.
In the context of your talk of future machines enabling us to probe BSM effects using this language of SMEFT, what do we get from high lumi LHC?
So many of these examples that I have showed you actually will not, the degeneracies we have seen will not be removed by high luminosity data. The reason is the way this LHC data is probing the combinations of Wilson coefficients means that even with a high luminosity, you will still have the same degeneracy. The point from introducing these other observables is that they will have a different sensitivity to different combination of these Wilson coefficients. So you really need a different observable, not just high luminosity, but you need a different observable to probe some of these combinations. So that's in the context of SMEFT.
Your talk is very impressive, but I'm confused why you have an uncertainty in the renormalization scale in all your QCD predictions. There is no real uncertainty. You can systematically eliminate the renormalization scale from first principles.
Yeah, this is a long discussion, and I don't think we should be having it here. So yeah,
No,
I mean, our way of estimating the theoretical.
I disagree. I think it's one of the most important things because if you eliminate the renormalization scale uncertainty, you greatly increase the sensitivity to new physics. And there's no, we do know how to eliminate the renormalization scale from first principles. In the case of the muon G minus 2, there's nobody ever puts in a guessed renormalization scale. We know what it is. You just simply sum the beta terms. In the
Okay.
case of QCD, you just sum the beta terms and it eliminates the scale uncertainty. So I'm confused why
That's an
this is
interesting
done.
question, and I think our committee is still thinking about this. What's the best way to, I mean, you have to provide an uncertainty in some way. There is an uncertainty in what we do. We
Well-
have to provide, how do we quantify it? How do we quantify
But
the
th-
missing
but
higher
this-
order
but-
terms?
But that's a totally heuristic uncertainty just to guess the scale. It's completely heuristic. And it'll give, in QED, if you did this, you'd be thrown out because there is no renormalization scale uncertainty. So
Thank you.
So why
Yeah.
do that, you know?
That's
I
a
think
good
people,
point.
I really would like to get into debate with people who really, they really should understand it. It's a gigantic literature on BLM PMC scale setting, and it works every time precisely just as you expect.
That's a good point. Thank you.
Yeah.
No, I wonder, you know, we were talking about this operate expansion in units, I mean, relatively to this lambda, I mean, new
SMEFT
physics
expansion.
scale, right? But however, no, not however, but there is also expansion in respect to, say, Q square or energy, whatever, which is not new physics, but, you know, just energy or momentum transfer, you know, in your process. And this kind of appears even in PDF, right? Because you have height width corrections, which 1 over. So when you have this expansion in 1 over square, it could be similar operator appears, right? Not which are not due to new physics, but just due to expansion in ratio of, say, transversal momenta to, I mean, to energy, and you have transversal distribution, which is related to the same stuff. So how it influences, you know, this analysis?
I haven't thought about it at all.
but you see what
I see what you are saying. Yeah. Yeah.
Okay, thank you.
Basically logs and x and higher bliss, right? So,
No, but you have 1 over lambda, but you also have, say, 1 over q, right? And it could be the same operator.
That's something to think about. Thank you.
I think we can thank all our speakers
Thank you.
and all the speakers.